several more complex examples of Dalton's law. In this video, we're going to review all of our previous concepts and increasingly complicated problems. Remember that this problem set is not all-inclusive. You should not be memorizing individual problems. You should be paying attention to the process that we use to work through the problems, and then applying this to all of your other problem sets that you have. This example is very similar to our previous ones. Here I give you percents instead of a picture though, but it's basically the same as the mole fraction picture that I gave you in the previous video. Just like with any problem dealing with percentages, and thanks to Dalton's law, we can now multiply each percentage by the total pressure to get our partial pressures. So using what we learned in our pictorial version of this question, try this on your own first, and then come back and we'll go over it together. So now let's look at this. We have our 1.20 atmospheres total, and we know what each percentage the gas is. For CH4, we can then multiply the 0.886, remember to convert it into its fraction form, by the 1.2 atmospheres, giving us a total atmosphere of 1.06 for the methane. We can do the same thing for ethane and multiply the 0.089 that comes out when we turn it into a fraction by the 1.2. Finally, we'll do the same thing for the C3H8. We'll multiply the 0.025 by 1.20 to get our final answer. Also note now that when you add all of these up, it should equal 1.2, give or take a bit for rounding errors. And if you do this, you'll see that we do get 1.2, and so it's likely that we did this correct. Let's move on to a more complicated example. Here we have two gases. They were originally in separate containers, and we want to know what the pressure is going to be once the valve is opened and they're mixed. We cannot just add the pressures here because you're not simply combining them into the same container. They were at different starting conditions. They had different starting volumes, different starting pressures. So to adjust for this, what we're going to do is treat each gas individually, as we did in the ideal gas law video. We'll act as if the pink one is expanding into the whole thing all by itself, and then we'll act as if the blue one is expanding into the whole container all by itself. And then we'll be able to add those together thanks to Dalton's law. So we'll start from our typical 2-point ideal gas law version of the equation. Remember that we're talking about each gas individually when we do this. And so our moles are actually going to be held constant because when we do this for the pink, our moles of pink will not be changing. When we do this for the blue, our moles of blue will not be changing. Our temperatures stay the same as well, and so we can cancel those out. This leaves us with PV equals PV. In each case, we're going to be solving for our final pressure, and so we can solve for our final pressure right away just to save us some steps. Now do this first for the pink, and then come back and watch the video if you need some help, or you can keep moving on and do it for the blue and watch the video for help if you need it. Let's solve for the partial pressure of each one separately, starting with the pink. We will fill in our values of 1 atmosphere and 1 liter for our initial starting values. Notice our final volume. It's 5. It's the total volume. It's often common for students to put 4 here. We are not putting the pink one into the container that the blue one was in. We're allowing it to expand across the entire container, so you must add them together. This gives us our final partial pressure for the pink. Now do the exact same thing for the blue. For the blue one, we're going to do the same thing. Our values are just going to change since we're using the other gas. Our pressure now will be the 2.5 atmospheres. Our volume, initially, the 4 liters, the container that the blue is in. But our final volume is going to be the same as it was for the pink because it's allowed to expand across the entire container. Once we get all of this, we can now get our final partial pressure of our blue. Now our last step. We need to add those two values together in order to get the final pressure. This is the Dalton's law part. If we add up our 0.2 plus our 2, we get our total pressure of 2.2 atmospheres. This one is a pretty common example on standardized tests, and so I think that it's a good sample question to use. There is one extra piece of information that you need to know. We won't go into the details of it, but you know that when you have a volatile substance like water, it is going to evaporate a bit. In a closed system, that means that part of the pressure that exists in the container will be from the vapor of the liquid, in this case the water. So let's first just look at the setup. Here we have a reaction of some sort occurring, and to measure its progress, we can collect the gas that evolves from the tube over water. This collection tube would originally be completely filled with water, not like it is here, half filled. As the reaction creates oxygen, it displaces the water, pushing it down as we see in this picture. The collected gas is a combination of the evolved oxygen from the reaction, or whatever other gas was evolved, and water. The collected gas is a combination of the evolved oxygen and the water in the form of water vapor. Now let's talk about how to solve the problem. Since we are only curious about the oxygen, and then we're going to change its values, and in this case, the initial values given have both oxygen and water vapor, we need to use the partial pressures to solve for the partial pressure of oxygen. To do this, remember how Dalton's law works. The total pressure is equal to the water vapor plus the oxygen, and that this must be equal to the atmospheric pressure since it's what is pushing down the water and up into the tube. Of course, if we rearrange this, we can get the partial pressure of the oxygen being the total minus the water vapor. This gives us the partial pressure of oxygen at 913.8 millimeters of mercury. Let's check and make sure that this makes sense. We know that the partial pressure of oxygen has to be less than the total pressure, and it is, and so that's a good sign that we've done it correctly. Of course, this doesn't give us our final answer since it's the initial set of conditions. Now let's change those conditions to get the final answer for what we're looking for. So now we need to use our ideal gas law in the two-point version to change from our initial set of conditions to our final set of conditions. However, to do this, we need to make sure that all of our units of pressure are the same, and they are. They are in atmospheres, but that's okay because they're both in millimeters of mercury. So we can now convert to our final set of conditions. I again kept the equation relatively separate in order for you to be able to see where all the numbers are coming and going from. So now we can fill in our values. We fill in our millimeters of mercury that we solved for on the last slide into our initial conditions, and our 7.28 into our initial conditions, and we divide by our initial temperature of 25 degrees Celsius converted into Kelvin. From here, we'd fill in our new temperature value and our new pressure value in order to solve for V2. Here we get 8.51 liters, and we have our answer. It's a little bit hard to actually go about checking this value with what makes sense, given that we have multiple changing conditions. Now let's look at a couple more examples that have chemical reactions in them. Here, I give you the problem to take a second and read it, and I give you the chemical reaction that goes with it. I ask you to calculate the percent yield. Remember that the percent yield is the actual yield over the theoretical yield. We can do this in either grams or moles. I generally prefer to do it in moles. So now we need to use the material that they gave us to find out how many moles of nitrogen are made, and the moles of the nitrogen theoretically possible based on the amount of reacting hydrazine. Let's start with the actual. To find the actual, we can use PV equals nRT. We have volume, temperature, and pressure, and so we're able to calculate the number of moles using the ideal gas law. So we will fill into PV over RT to get this value, being careful to check that all of our units are correct to calculate our moles of nitrogen. Given all of these values, we can fill in and we can get our final amount of moles. This gives us our numerator. We now must use the stoichiometry that we learned in previous chapters to calculate the theoretical yield. For the next part, we can calculate how much we would produce if every bit of it was converted as expected. The grams of hydrazine can be converted into moles of nitrogen by first converting to moles of hydrazine, and then to moles of nitrogen. From here, we get our values for our moles of nitrogen that we would theoretically produce. Our very last step is to actually fill this in and get our percent yield. Here, we know our theoretical value, and we can fill in to our percent yield. Our actual number of moles is 0.0310. Our theoretical is 0.0765. We can fill this into our value, multiply by 100%, and get our yield of 40.5%. Let's do one more example with chemical reactions. This one is a really pretty long problem, but it's nothing that we haven't done before. So take a moment and read the question, and think about how you'd go about solving it. Pause and come back when you have some idea of what you might do, or try to solve it yourself and then come back. So this one has 3 basic parts, and at its heart, it is a limiting reagent problem. However, as we remember from that chapter, to do a limiting reagent problem, we must have everything in moles and then have the equation relating them. This problem also asks us to report the values in pressure. So it gives us pressure and asks us to report in pressure. So what this means is that we're going to start our problem by converting everything into moles. From here, we can do the limiting reagent problem exactly as we used to do before ideal gas laws came into play. And then we can convert back into pressures. It's really very similar to how we do limiting reagent problems with grams, except that instead of using the molar mass on both sides, we're doing the conversion using the ideal gas law. So using the ideal gas law, we're going to convert our initial values given into moles. So take a moment and do this on your own first before going on. We have the initial values for each bulb given separately. If we use our ideal gas law for moles of NO, we fill in our 0.6 and our 6 liters. We divide by our R and our T. From here, we get 0.147 moles of NO. We can do the same thing for NO2. We fill in our initial pressure, our initial liters, and our R and our T, which gives us our initial moles of oxygen. That's exactly what we've done in previous videos. Now that we have our moles of NO and our moles of oxygen, this becomes a limiting reagent problem like you did in previous chapters. You wouldn't even, if I'd given you this values, you wouldn't need to know the ideal gas law at all to do this. So let's do this by comparing the amount of reactants that we have. If you remember back in the limiting reagent problems, there's many ways that you can do this, and if you need more help, spend some time on those videos. Here, if we look at our coefficients in our equation, we can see that for every 1 oxygen, we need 2 moles of NO. Let's look at our values. We definitely do not have those values, right? So once again, for every 1 mole of oxygen, we need 2 moles of NO. We don't have that. This means that NO is our limiting reagent. Now, of course, you can do this in one of the longer ways that we talked about when going over limiting reagents if you like, but we can do it just from this as well. Now, what does this tell us? This tells us that after the reaction has completed, our moles of NO is going to be 0 moles. Now, if we don't have any moles of a gas, its pressure is 0 as well. So we have one of the 3 done. We can now use the limiting reagent, or NO, to see how much of the NO2 we have left, or how much of the NO2 we are going to create, and how much of the O2 is left over. We will start with our amount of NO and convert this into moles of NO2. We do this by using the mole ratio in the equation. This means that we have 0.147 moles of NO2 created, since it is a 1-to-1 or 2-to-2 ratio. Now, the oxygen is a little more complicated, because we need to use the NO value to calculate how much oxygen is used up, and then subtract that from the amount of O2 that we have. We'll use the mole ratio of NO and O2 to convert to the moles of O2 used up. From here, we can subtract that quantity from the initial amount of O2 that we had, the 0.153 moles that we found in the earlier slides. This gives us our value of O2 left over. So we found our value of O2 used up by using the limiting reagent, and then we subtracted that from our initial value. We now have our moles of NO and O2. We've finished the bulk of the work for this problem. We simply have to convert this into pressure. Now, of course, this isn't at standard conditions and pressures, and so we can't use the 22.4 conversion factor that you might be tempted to use. We have to use the ideal gas law to convert to pressure. Using P equals nRT over V, or in other words, the ideal gas law, we can get our partial pressure of NO2. We fill in our moles of NO2 that we found on the previous slide, our R, our T, and our V. Notice here our V is the volume over the entire container because we allowed them to mix. This gives us our final pressure for NO2. Remember, we don't have to do this for NO because we had 0 moles present, and so we have 0 partial pressure. We can also do this for our moles of oxygen. We fill in the moles of oxygen that were left over on the previous slide, our R, T, and V, again using the final V of the combined flasks to get our pressure of oxygen. From here, our last and final step is simply to add these up to get our final pressure. As a quick reminder, and I suppose a wrap-up and review since this was just a video of many examples, with all of our example problems, you need to think about the process for getting there and be able to apply it to other problems. You aren't going to necessarily see the exact same problems on the exam, so make sure that you understand each reason why we did each step of the equation, that you understand the problem holistically, and that you can use this to solve other problems.